Hey, well, welcome to the PPPAI webinar. We're continuing our series. I think this is the last one in the series on high resolution climate modeling. And today we have our visitor from ECMWF, Chris Roberts, and he will be presenting on EuroAtlantic weather regimes and teleconnections and ECMWF reforecasts. And we really thank you for making time today to come and speak with us on this topic. Thanks. Go ahead.
Oh, you're welcome. All right, thank you very much. So from the introduction, this talk is looking at the representation of EuroAtlantic regimes and associated teleconnections and how these weather regimes in the North Atlantic and Europe are related to interannual and intraseasonal variability in the tropics and how they're affected by these tropical extratropical teleconnections and how the frequencies of regimes are modulated. It isn't really a talk on high resolution, but I will talk about resolution sensitivity or lack of resolution sensitivity, and I can comment on a bit on how this affects our strategy for subseasonal forecasting at ECMWF. So this first slide is really some motivation onto how we use this concept of regimes at ECMWF. So particularly during the extended winter season, which is what the results I'm going to discuss today, so thinking October to March, the atmospheric variability in the North Atlantic and Europe can be quite usefully characterized by these transitions between some finite number of large-scale quasi-stationary flow patterns, often termed weather regimes, and S2S forecasts, so forecasts at around 2 weeks to 2 months lead times. We use these regime forecasts operationally because they've been shown to provide some useful early warning of cold conditions over Europe. These three plots at the bottom are from a newsletter article by Christine Grams and others a couple of years ago, but they're just three different ways of presenting the same forecast information, but with slightly different emphasis either on geographic information or uncertainty or categorical information about types of regime. So in the bottom left, you can see this is an ensemble mean forecast of geopotential height. And you can see there's a low centered over Iceland and Greenland and high in Southern Europe. So this is characteristic of what we'd call a zonal flow regime or the positive NAO. The middle plot is showing the same forecast, but now it's showing some sort of ensemble probabilistic information as this density map in this phase space spanned by the first two leading EOFs of geopotential height anomalies. So you can see here that on the x-axis, it's this first EOF, which is representative of NAO positive or NAO negative conditions. And similar to the first plot, you can see that this is this forecast is weighted towards positive NAO conditions. And then lastly, this is another way of visualizing the same information, but now showing this the ensemble members categorized into each of these four different regimes. And again, you can see that in this forecast, there's a clear signal of positive NAO conditions throughout the first few weeks. And these regimes, they're usually defined by applying some sort of clustering method, often to some reduced space spanned by the first few EOFs. What I'm going to talk about today is focusing on these four different, often called the classical EuroAtlantic regimes, and these are derived using a k-means clustering applied to geopotential height anomalies over this subdomain. And here you can see them defined for the ERA 5 reanalysis. So the black lines are contours for geopotential height anomalies for the regime composite means, and the shading is for the associated 2-meter temperature anomalies. And again, you can see this positive NAO, so it's associated with warmer and typically wetter conditions over Europe. And similarly, the negative NAO is sort of like the reverse image, so cooler and typically drier conditions over Europe. And then we also have a Scandinavian or European blocking with the high centered over Northwest Europe, and then a sort of Atlantic ridge regime with the high centered further over the central North Atlantic. But really importantly, especially for S2S forecasts, these regimes and their frequencies can be modulated by other modes of variability. And in particular, the Madden-Julian oscillation. So this is one of the most important sources of skill at S2S lead times. This provides a source of Rossby waves, which generated in the tropics can propagate along waveguides and then influence the high latitudes where wave breaking can affect regime development and transitions between regimes. And there's kind of two distinct pathways where, that this can occur by. So this is a causal network from a nice paper by Elizabeth Barnes and others a few years ago, emphasizing the nature of these two distinct causal pathways between the MGO and the NAO. So there's a kind of a direct tropospheric pathway where you have Rossby waves steered along the waveguides of the tropospheric jet. And then there's this indirect pathway in which the MGO first, you have an influence on the stratospheric polar vortex, and then there's a downward connection between the polar vortex and the NAO. And these mechanisms have been described in a few papers, and there's a list of references down below. So what I'm looking at here is data from ECMWF reforecasts. This is from our subseasonal or extended range forecasting system. And I'm showing here results from two different versions of the same system. So the first is our operational reforecasts. These are run in the year 2022, but the reforecasts, so the hindcasts, cover the 20-year period 2001 to 2021. Each forecast date has 11 members, runs for 46 days, has 920 start dates over these 20 years, and it's equivalent to about 1,300 years of data. And the way this is configured operationally is for the first 2 weeks, we run at the same resolution as our medium range ensemble. So this is 18 kilometers. And then this is extended at a slightly lower resolution of 36 kilometers for the next 30 days. And these are all coupled to an ocean sea ice model, which is run at the eddy permitting resolution of 25 kilometers. The other data I'm using is a lower resolution system, and the motivation for this is we want to have a robust sampling of both the regimes, but also how they're modulated by different interannual phases of interannual variability to get good sampling of ENSO or La Nina versus El Nino states. And so this lower resolution system, it's the same cycle, it's our currently operational cycle, the exact same physics and configuration, 11 members, 46 days, but now it's 480 start dates run over a 41-year period covering 1980 to 2020. This is run from day one with a resolution of 50 kilometers in the atmosphere and 100 kilometers in the ocean. So it's really, it's obviously far cheaper to run this for RD purposes, but the motivation is to improve our sampling of this interannual variability. And just to compare these two systems, so this is the bivariate correlation for the Wheeler and Hendon multivariate MGO index. So in our S2S system, we have MGO correlation skill exceeds 0.5 for more than 30 days. And the black diamonds with the error bars, this is the skill in our operational system. And the red line is the skill in this lower resolution system. So they're extremely similar. And although I said this isn't really a talk on high resolution, the comment I will make is the work we have done evaluating the benefit of much higher resolution at this timescale has generally shown very little effect. So our next big upgrade, which is going to be cycle 48R1, we have a new supercomputer. The way we are choosing to spend our resources to meet user demands is to, instead of initializing subseasonal forecasts twice a week, Mondays and Thursdays, we will now spend that extra computational resource by initializing every day and having 100 members in the real time rather than 50. So in our experience, there's not so much benefit for the extended range at boosting resolution from, say, 50 to 15 kilometers. It's a rather modest impact. And this is a similar plot showing the skill in the different regimes. And obviously there's far less skill, so correlation skill falls below 0.5 within 14 to 18 days. And again, the low resolution system is generally consistent with our operational system. Although I would say here it's much easier to see that I would say that during these first week or two, the higher resolution system is better. So at NWP and medium range timescales, higher resolution is demonstrably worth it. But at these extended range, so weeks 2 to 6, it's less. It's not as obvious that you've as much to gain if you compare that with how you would spend your resources on larger ensemble sizes or more frequent forecasts. Okay, so moving on. So the way I've structured this is I'm first going to show several things that the model does extremely well, and then focus on some of the issues that we have. So this is now just looking at the same regime structures. So again, geopotential height anomalies in the black contours and the 2-meter temperature anomalies in the shading. So the top row is in ERA5, our reanalysis. The middle row is in our reforecasts for the first week, and the lower row is our reforecasts for week 6, I think. And generally, the spatial structure of the circulation anomalies and 2-meter temperature anomalies compare extremely well between our forecasts across all S2S lead times. There is a slight decrease in the amplitude of the temperature anomalies, but still, I was quite surprised by quite how well these agreed. We also see extremely similar results if we plot the same for precipitation anomalies. And using this is for the operational system, but if we use the lower resolution system for the same dates, we get, again, something that looks remarkably similar. We can also look at the climatological regime frequencies. And here, this is just averaged across all start dates. And the reforecasts are within the sampling uncertainty of ERA5. We can also look again at frequencies versus forecast lead time. And again, they're actually quite stable and in very good agreement with ERA5. I think the one noticeable difference is that at the longer lead times, maybe weeks 2, 3, 4, you start to see the model slightly underestimate the frequency of the positive NAO and slightly overestimate the frequency of the negative NAO. And we can also look at the regime frequencies conditioned on the initial regime. So this plot in the top left, this shows it's the frequency or the probability of each of the 4 regimes. So in red is NAO, the sort of pink is negative NAO, light blue is blocking, and the dark blue is the Atlantic Ridge. And this is all conditioned on the initial regime being a positive NAO. And the solid lines are the reforecast and the dashed lines are the ERA5. So based on this comparison, our reforecasts are doing extremely well, both at capturing the persistence of these regimes, but also the probabilities of other regimes, so the transition to different regimes in the sort of 20 days following. So this top left plot is the initial regime as the positive NAO, but then we get very similar results for conditioned on the other regimes. If you start to look at the details, you will see some differences. But again, I was quite surprised by how well our reforecasts seem to do, looking at the frequencies just conditioned on an initial regime. So where the forecasts don't look so good, though, is when we start to look at these regimes conditioned on phases of intraseasonal or interannual variability. So there's a couple of quite influential papers, maybe 15 years ago. So this paper by Christophe Cassou, another paper by Linnetal, and they were the first to show that how the wintertime EuroAtlantic regimes, and particularly the NAO, can vary a lot with in terms of the phase and the lag for the different MGO phases. So, for example, the positive NAO is much more is more likely to occur in the maybe 5 to 15 days following MGO Phase 3, when you have convection in the Indian Ocean. And you can see that here in this panel, top left panel, which is for ERA5. So on the y-axis is the different MGO phases, and the x-axis is lag in days. And the squares are some measure of the significance using a bootstrap resampling across the different start dates. And our reforecast can capture the kind of phase lag structure of this modulation of frequencies, but they underestimate the magnitude. So there is an increase in the probability of positive NAO, but it's not as high as the increase we see looking in reanalyses. And we see a similar story looking at the negative NAO and the Atlantic Ridge. So the reforecasts do a good job at capturing the kind of phase lag structure, but underestimate the amplitude. The blocking regime, so this European Scandinavian blocking, it's far less obvious that there is a strong modulation by the MGO for this. This pattern and which regions are significant are really sensitive to the time period you use. So if you do this just for the last 20 years, you get quite a different result here. So these results, though, are very systematic and quite robust, looking at the positive and negative NAO. So it's those two I'll focus on for the remaining slides. And these interactions I just showed that the MGO modulates the regimes. There's a nice paper by Rob Lee and others a couple of years ago showing that these teleconnections between the MGO and NAO are also strongly sensitive to the ENSO background state. So the first one, the first two panels I'm showing, this is looking at this positive NAO response to the MGO. And this teleconnection, which is, they relate to a tropospheric teleconnection pathway, is far more active during the El Nino season, when you've got this strong connection between the exit region of the Pacific jet and the entrance to the North Atlantic jet. But this modulation is suppressed during La Nina, so you don't see this, this significant amplitude modulation of the MGO teleconnections during the La Nina. We can also look at the negative NAO, and in this case, the interesting signal is that during La Nina conditions, this response of the negative NAO is shifted more, the increased likelihood of a negative NAO is shifted more towards later MGO phases and longer lag. So it's shifted down to more into the sort of days 15 to 20 following MGO phase 7 and phase 8. And this is linked to an increase in the strength of a stratospheric teleconnection pathways. So the MGO influencing the or weakening the polar vortex, which then has an impact on the probability of a negative NAO. And what we can do is look at the same in our reforecast. And although our reforecast, you get some slightly different statistical significance, the underlying patterns are extremely similar. So as well as underestimating the amplitude of this this modulation by the MGO, they also seem to be they are not sensitive to the ENSO background state, unlike in the ERA5 reanalysis. And we can also similarly look at how these regime frequencies are modulated by the stratospheric polar vortex. So the previous work has shown that generally stronger polar vortex events are associated with a more frequent positive NAO, and weaker vortex events are associated with more frequent negative NAO. And the most extreme events, something like a sudden stratospheric warming, these are a weaker vortex event and have also been linked to negative NAO conditions. Generally, the blocking and the Atlantic Ridge regimes show far less sensitivity to the polar vortex, so these are not shown. But down in the bottom left, you can see here, this is the positive NAO, the probability conditioned on whether or not there's a weak or a strong or a neutral vortex. And here, the solid lines are for the reforecasts, and the dotted lines are for ERA5. And similarly, this is for the negative NAO, so you have almost the inverse relationship now. And what I would say here is generally this modulation by the vortex state seems to be quite well represented in our reforecasts. If we have a problem in this stratospheric connection, which I'll show in a minute, I think it's more related to the response of the polar vortex to the MGO than it is to this downward relationship between the polar vortex and the North Atlantic regimes. So I've done a little bit more work to look at these tropospheric teleconnection pathways. So there's been several previous papers by my colleagues at ECMWF, including Frederick Guittard, showing that S2S models, not just the IFS, but S2S models in general, underestimate the magnitude of these MGO teleconnections. One way you can try and look at this a bit more is use something like a wave activity flux, which are useful because they give you some indication of both the magnitude and the direction of energy propagation associated with stationary Rossby waves. There's some details here on the methodology, but these sorts of tools have been used before to look at both models and investigate pathways and mechanisms in reanalysis data. And this is the sort of thing you see. So here's an example. This is showing a composites for MGO phase 3, 1 to 5 days following MGO phase 3. Firstly, for all forecast dates. And there's a few things I'll just point out in. So on the left is ERA5, and on the right is our reforecast. So for these cases, you get the strongest outgoing long wave radiation anomalies in the Indian Ocean. So this is indicative of where we've got convection. And generally, the reforecast reproduce this both the spatial structure and amplitude of the OLR anomalies quite well, which is suggesting we're doing quite a good job at the MGO. We also capture this clear separation of the Atlantic and Pacific jet streams. So the way I've highlighted that here is this red contour shows the 30 meters a second climatological zonal wind. And then the main sources of stationary Rossby wave activity are generally sort of to the north of the Indian Ocean and in the exit region of the Pacific jet. And our forecasts underestimate the amplitudes, but we're getting the location of these features. But what we're missing is this wave train that propagates from the North Atlantic into the, from the North Pacific into the North Atlantic. And this connection between the North Pacific and the North Atlantic is also missing when we really focus on the El Nino initial conditions, where you see it's much stronger in ERA5, but again, it's missing in our reforecast. So when we stratify by, when we just focus on these El Nino initial conditions, again, we do a reasonably good job at capturing the OLR anomalies. We also get this stronger connectivity between the Pacific and the Atlantic waveguides. So a sort of a naive hypothesis might have been, well, we're not doing a good job at getting the tropospheric pathway and the teleconnections because it's a mean state bias. It's a problem with where we've got the jet stream or the strength of the meridional vorticity gradients or some other property of the mean state. But in general, it's very difficult to demonstrate one way or another that the errors we have in the mean state are sufficient that you would expect some qualitative difference in wave propagation if you look at something like wave paths or ray tracing. So if it's not clear what the error is, but it doesn't seem to be a mean state issue in terms of the waveguide, and it's not obviously a problem with the MGO magnitude or the geographical structure of the MGO and its related anomalies in divergence or wave forcing. And then next, this is now looking at the response of the stratospheric polar vortex, focusing on the La Nina conditions following MGO phase 8. And there's been, again, lots of papers showing how vertical Rossby wave propagation can drive warming of the stratosphere and increase the probability of a negative NAO. And this paper I mentioned by Rob Lee and others, they also looked at reanalysis, so ERA interim, not ERA5. But they demonstrated that this stratospheric response is generally stronger. The stratospheric response to the MGO is stronger during La Nina conditions, and you can see this here on the top row. So in the top left panel, this is the blue shading indicates a weakening of the zonal winds, and the black contours are these are the temperature contours, so an increase in temperatures. So looking at all dates together, you do see this warming and weakening of the zonal winds. But when you look just at the La Nina initial conditions, you can see that the decrease in the jet speed and the warming is much stronger. We see a similar response in our reforecasts. We get warming, we get weakening of the zonal winds, but we underestimate the amplitude. And in particular, we underestimate the amplitude during La Nina conditions. So I would consider this these errors to be more substantial or more important than the errors we might see looking at this downward propagation from the polar vortex to the North Atlantic and European region. So to summarize, our reforecasts, they seem to accurately represent the structure, the surface impacts, and the frequency of regimes when we look at them climatologically. But there are some really substantial errors when we condition on modes of intraseasonal to interannual variability. And it's not obvious this is a problem related to resolution, at least looking at resolutions of between 50 and 15 kilometers. And it's a real priority for us because, in a sense, it means we have unexploited predictability. Our MGO predictability is very good, but we're unable to adequately propagate that information to the extratropics. And so I highlighted a couple of specific issues that we think are contributors to these conditional errors. So firstly, we're not getting enough wave activity stationary wave activity propagation from the Pacific to the Atlantic following MGO activity in the Indian Ocean. And this error is particularly severe during the El Nino conditions. We're also underestimating the response of the stratospheric polar vortex for the MGO during phase 7, phase 8. And this error seems to be most substantial during La Nina initial conditions. These errors are not easily explainable by biases, so errors in the climatological waveguide or the MGO forcing. So we really need to make progress in this and understand what's going on. And as I said, improving the representation of these teleconnection pathways is a priority for improving our forecasts in the extratropics. But we're finding it very difficult to make progress on this issue. It's something it's a long-standing error in the teleconnections, and it's present in many models, but it's a really hard problem to solve. But one thing I think might be useful is that if we start to stratify analysis or diagnostics by ENSO phase, it's quite an interesting way to try and maximize the signal, where the signal is the model error, to try and interpret what's going on. So I will stop there, and I'm happy to answer any questions.
Thanks, Chris. So let's open the floor now to questions from the attendees here. Just raise your hand and I'll call on you. Erin?
Hi, Chris. Erin Towler from NCAR. Great talk. And I love this idea of adding predictability by going straight to the weather regimes. I think that's really promising, and you showed a lot of great research for that. My question is, so when is it good enough? Like, what are the metrics that you're using to kind of say when you'll get far enough? Like, are you using these are you actually forecasting the weather regimes? Are you saying operationally, it's going to be a 50% chance of positive NAO? Or when will it get to the point where you can do that? Or are you already doing that?
So is the question, what are the products we provide operationally for weather regimes? Is that?
Yeah, I guess, yeah, I'm trying to explore the space a little. So yeah, if you have products already, I'd be curious about them and, and how you verify them, or where I could look to see.
Yeah, the plots I showed at the beginning, I think, are all operational products. So we have this, I mean, obviously you can look at ensemble mean anomalies and say, well, this looks like a positive NAO type condition. I think this diagram that breaks things down into the phase space of positive or negative NAO and a positive or a negative blocking. So this is like the first two EOFs. This is something that's provided operationally. So you have these density maps in this phase space. I think they're merging information both about because it groups together several lead times over a week, as well as over the 50 ensemble members. So you get some sort of estimate of where you are in that phase space at different lead times. So I think we do that week by week. I think we also have, for that same diagram, kind of trajectory plots, so like spaghetti plots showing the evolution of each member in that phase space. And then this also this categorical product at the end, which I can just, let's see if I can go back to. This is also operational. So this one here in the bottom left. So this is, it's showing also the verifying analysis as well. So it's got, for each member is allocated one of the regimes. And then there's also where you would allocate the ensemble mean. So it gives a sense of not just the most likely regime, but also what are the likely transitions. So it looks like in this case, it's going from positive NAO towards an Atlantic ridge and then maybe back to the positive NAO. However, there's a whole zoo of different ways of describing regimes. And this is for a particular 4 regimes over the EuroAtlantic for the wintertime. But I think there are other definitions for year-round, which then allocate to, I think, 7 different regimes where they're usually, I think, 4 or 5 different types of block. So you might have a high latitude block, which looks a bit like the negative NAO, and a low latitude block. And sometimes people put persistence criteria on. So you might only allocate a regime if it's in that same regime for more than n days or something during the forecast. But yeah, we do this, and I think it's just a different way of exploring the of presenting information in a way that some people find useful. So obviously you lose geographical detail, but you maybe gain a different way of looking at uncertainty or trajectories in terms of transitions between different regime types. I've also seen similar plots to this one here, where it breaks down, each member shows the sequence of regimes in a member. I think that's another one we produce operationally. So you can see what are the most likely transitions, even if those transitions occur at different lead times.
Excellent talk. By the way, Matt Newman just showed up. Oh my gosh. Anyway, yeah, so I'm curious if you can go back to your slide on, I think it was like MGO phase 3 plus NAO positive. Yeah, keep going back.
This one.
Yeah. So this is really interesting. I wonder though, if you were to look at the members in the reforecast, whether you could get a better match to that error pattern. Like if you were to look at it on a per member basis, like would any of them come close to the level of wave activity that you see there?
Yeah, I thought about this. I think it's not as unfair a comparison as it might seem, because each of the members, the MGO phase is detected at each lead time in the member, and then the composite is derived from the n days later for each member. So it's not like saying that MGO was in this phase at the initial condition, and then we do all the composites at the different lags. It's done on a per member basis, but I understand what you're saying. I need to go back.
You could do like a spatial pattern match for each member and see if it is better than what you.
Yeah, I mean, another thing I thought is if we kind of find the members that best match this wave activity flux, what does that do to the NAO composites? Because it could be, are there any of them that are doing a good job, or is it? But in a sense, they are both averages over many cases. It's just that there are 11 times as many cases in the reforecast. So another thing you could do that's maybe fairer is just do it on a single member across the same dates.
Yeah, I mean, I think this is really interesting. I also think about it in my own work as how to fairly represent the spread of the ensemble. And I think trying to like visualize that and represent it is always a challenge, but I think it's worth doing.
But my gut feeling is that this issue with the teleconnections and generally underestimating the extratropical response to the intraseasonal tropical variability is a fairly well established and generic problem in the models, and I don't think it's something that will just
I tend to agree. It would just be nice to kind of like show that.
The other way this manifests is actually if you want to look at teleconnections in a model or a seasonal forecast or an extended range forecast, you often need a massive sample size to get a significant teleconnections. So you need 10 members and 20 years. But in the reanalysis, we only need one realization, and that's often enough for statistical significance. And I think that's partly because the signal is just bigger. But yeah, it's an interesting question. I don't have the answer to hand though.
So we have a few other hands up, so I want to call you guys in order that you raise them. So Bao.
Yeah. Thank you, Chris, for a very nice talk. I have two questions. One is you mentioned that modular solution has a relatively minor impact, but you have decided to increase the ensemble size from 50 to 100. I'm just curious about, you know, this most of the modern center cannot probably afford this 100 ensemble members. So what is most, do you have a recommendation? So what is the number that the scale will be saturated, like a 30 or 50?
I mean, it depends on what you're particularly interested in. I think one of the motivations for having 100 members comes for things like tropical cyclone density plumes. So when you're in this 2D space where you're trying to come up with strike probabilities for a tropical cyclone, it's really helpful to have more members to plot that. It might not have a huge impact on, for example, correlation skill for the NAO, but in extremes, I think, for extreme events, it's quite useful to have these extra members to populate the tails and things. In terms of probabilistic skill, you can, I mean, there are things like the continuous rank probability skill score. There are theoretical, or you can write down with a pen and paper, what's the increase in the CRPS you expect by increasing ensemble size from 50 to 100. And that's pretty much what we see in the probabilistic scores. So a lot of our testing that we do and our verification, we actually only run small ensemble sizes. We run with maybe 10 members and apply a correction, so we get unbiased estimates of the probabilistic skill. So you can kind of estimate what you expect the probabilistic, how that probabilistic skill would change for things like the Brier score and the CRPS, just with a pen and paper. And that's for most atmospheric variables. I think that's what we see. For other things like, I know at seasonal timescales, people are really interested in large ensembles because they think they have there's a problem with getting the signal in the models. The signal's too small, so it's helpful to have massive ensembles. At the sub-seasonal range, I think that's less obviously an issue, but the benefit of the ensemble is in better characterizing that PDF. It improves our estimates of improves our probabilistic skill estimates, and it helps us sample for extremes. But obviously, like, yeah, people have to choose how they spend that available resource. So when I said that so you see here on this table, our current operational configuration is to run for days 1 to 15 at high resolution, which is actually just the medium range ensemble, and then we extend it. But each real-time forecast is accompanied by a 20-year reforecast. And at the moment, because our medium range and extended range systems are tied together, we have to run these reforecasts using this first 15 days at high resolution and then the extended resolution. And it means as a disproportionate amount of our HPC is spent on the reforecasts because we're coupled at the medium and extended range. The next cycle, they will break. So our extended range system will run from day 1 at 36 kilometers. Our medium range system will run from day 1 at 9 kilometers. So there'll be a 50-member 9-kilometer ensemble running for 15 days and a 100-member extended range system running 46 days with 36 kilometers. And that means some people might want to use that dual ensemble. But what that means is our reforecasts now are less, the fraction of HPC we spend on our reforecast is reduced because we've kind of separated concerns. The reforecasts are far less important for the medium range. They are used for calibration, but they can run with a small ensemble size. Whereas for the extended range, we use them a lot for calibration because our products are anomaly based relative to a hindcast climatology, and we also use them a lot for skill estimation. Sorry, but this is a game everyone's got to play. They've got to decide what's the best use of resources and how these things tie together. And this is kind of a change from our current seamless strategy because we're no longer just taking the end of our medium range and carrying on. We're just running a separate system, but it allows us to do something a bit different with more members. And so on that question, resolution is definitely important for the medium range. That's why it's going to 9 kilometers, but it's less important for the extended range, which is why we stick at 36 but run with bigger members.
Okay. I have another question. You said the teleconnection is very challenging in predictions. I think that is also partially related to the mean state drift, especially in a coupled model system. So have you considered some like a mean state adjustment, at least like a SST or atmosphere mean state adjustment?
For RD experiments, yes, we've done this. We've done things like bias correcting the SSTs. Currently running an experiment where we're bias correcting the stratospheric temperatures. So this is actually using infrastructure that's from our data assimilation system. So we have something called weak constraint 4D VAR, which outputs as a estimated during the minimization is an estimate of the stratospheric temperature bias. And we can apply that in a forecast forever if we want. Probably eventually it will probably stop working, but we're going to see if that helps. But at the moment, it's not on the cards. We've been quite purist in the past that our coupled forecasts are forecast, and we don't introduce sources or sinks of from bias correction terms. But I think the landscape is changing at the moment. This big shift towards machine learning, publishing is going to come as a bit of a challenge, and we may see in the future different ways of us providing either online corrected forecasts or calibrated forecasts that try and account for some of these things. Because the teleconnections, you could see that as being essentially a flow dependent bias, which is something that we could perhaps correct for. You could have an AI or a machine learning bias correction that is flow dependent, and it knows that in a MGO Phase 3 El Nino conditions, we're likely to underestimate this response. So that's another thing that we may investigate in the future.
Okay, yeah, thank you very much.
We do have one more question, and then before we wrap here, so Sanjeev, go ahead.
Chris, this is nice presentation. This is Sanjeev from Auburn. Since you did show us the geopotential height as well as temperature, or like referred to the precipitation also. So geopotential height has a less signal, or at least if you do kind of signal to noise ratio paradox in these kind of seasonal or decadal, geopotential height will show you a lot of signal to noise ratio paradox compared to the temperature or precipitation. So what's the conclusion that you draw about the ensemble size or the resolution? Is it dependent upon the variable of interest like a geopotential height versus precipitation, or some of these conclusions are independent of the variable of interest?
I would say that the decisions we've made at ECMWF about ensemble size and things, both for medium range and the S2S, they're not driven by a consideration of signal to noise paradox. I think this is something that is far more evident with longer time averages, so time averages over seasons, which I think acts as another way of increasing sample size, and at longer lead times. If you do this sort of the statistics that are used to estimate things like the ratio of predictable components or other measures of potential predictability, it's not obvious looking at these like NAO scores as a function of lead time by day that there's any particular issue. And I think it's probably because at these lead times, there is just a lot more skill. There is a lot more signal and skill. And it might be that at these lead times, we're primarily doing, like I showed this skill in the NAO and the different regimes, it goes out to maybe 2 weeks. A lot of that's probably the initial value part of the problem that we're predicting. I think for these sort of seasonal type signal to noise paradox ideas, it's more related to the slower varying properties and maybe not communicating from, I don't know, but the teleconnections could be a part of that. I'm not sure, but it's the decisions we've made about ensemble size are driven more by what we know they will do for skill or for sampling of extremes, rather than any sort of sense that we've got the signal, but it's too small and we need a massive ensemble to capture it. So yeah, it's tricky. But for most metrics that we do use, so we think a lot about reliability and our forecasts are calibrated. They generally are. So the error in our ensemble mean, or the RMSE in our ensemble mean, generally matches the spread in our ensemble over longer periods. So yeah, I don't know. Some people say that that you do see the signal to noise paradox S to S. I just think it's less evident to me if you're looking at it as a function of lead time each day. I'm not sure that answers the question, but sorry.
Okay, thank you.
Okay, well, we're going to wrap there then with the balance of our time for discussion of the panel. So a round of applause for Chris. Thank you for presenting and taking the time out here, out of your evening to join us today. So take care.